Hello everyone again, and this is the second part of the video about approximate integration, where we are going to consider more methods of integrating the function approximately. Before I start talking about all these rules, you already remember that we can use left-hand rule to estimate the sum, right-hand rule, and midpoint rule, right? Let me kind of draw the picture of some arbitrary function to explain you how we actually choose rules. Imagine that we have a function looking like this. That's my actual function. Well, the idea of approximate integration is to represent function as something familiar to us for which we do know the area, the rectangle, or some other object. For example, guys, curvy function like this can be represented as a piece of parabola, right? Now let's imagine there are 3 points, and we consider it's a piece of parabola like this. Do we know how to find the area under parabola? Definitely we do know. We know how to integrate parabolas. They are just polynomial functions, very easy to integrate, right? If you cut a little piece of this function and increase it, you are going to see that your function is not curvy anymore. But it looks almost straight like this. And if you consider your function and cut a little piece of it, like right over here, and increase it, you're going to see that function actually is going to look almost like that. Change is going to be almost flat. Well, guys, why I'm doing these 3 pictures? If you are going to do very, very small steps, your function for each of these steps is going to look like a straight line. And straight line can be represented as a left, right, or midpoint rule. And we can kind of continue working with rectangles looking like this, right? But if you consider slightly bigger steps, maybe it makes sense to kind of take in account that function is actually looking more like an inclined line, right? And here we can consider, instead of rectangles, trapezoids looking like this, and estimate area by trapezoids. Or we can even keep like a curve of the function and consider relatively bigger steps and use actually parabolas to estimate, because we do know area of the parabola. We do know area of the rectangle. For rectangle, we know that area is going to be what? Delta x by fxi. So delta area here is delta x by fxi, right? What is going to be area here? Well, area of trapezoid, if you do know 2 sides, is going to be what? Let's call it fi, and this side fxi plus 1. So we do have average of f of xi plus f of xi plus 1 divided over 2 and multiplied by the height. Just normal trapezoid is going to look like this, right? For parabola, formula is going to be more complicated. We actually need to develop it. We are going to develop it. So guys, first one is going to produce for us M rule. Sorry. Go back to press something wrong. So this picture is going to create for us, so that's M rule. M rule is making flat out of actually curvy function. T rule, trapezoid rule, is going to consider that the function has like different ends. And the one which considers parabola is going to be called Simpson's rule or as. For right now, I want to discuss a little bit T rule, and then kind of at the end of the lecture do Simpson's rule, okay? So how T rule is going to look in general. Here we do know that we just add up all the values of the middle of the intervals and multiply by the step, and it's going to produce integral for us. What are we supposed to have for trapezoid rule? Well, for trapezoid rule, we are going to have the sum of areas, and I'm going to kind of write them down like what we have. The area, the total area is going to be the sum of these little tiny areas, right? And that's going to be equal h. I'm going to take this h outside of all these formulas. And I'm going to start f of x0, the first point, plus x1 over 2. And the next trapezoid, we should produce a bigger picture. Like, let me do the picture. I want to be more mentioned at the picture. And we have several trapezoids here. So, for example, this is my first trapezoid, the second trapezoid, and the third. So it's x0, x1, x2, x3, and we are going to estimate the areas of those. Okay? So we are going to have f of x1. Well, it's just like the x1 works for the first trapezoid and also for the second trapezoid, because for one it's like bottom of the trapezoid, and for one is going to be the top of the trapezoid. 2 over 2, and until we reach the very last trapezoid, which is going to be f of xn minus 1 plus f of xn over 2, right? If we simplify this formula, first we're going to take this 2 outside and write down h over 2 here. Now inside we are going to have f of x0 plus f of x1 is going to be repeated twice, so 2 f of x1. And then f of x2 is going to be also repeated twice. And until the very last one. The last one is not going to be repeated twice because there is nothing behind it. So we are going to just have f of x and only one value. So that's a general formula of trapezoid rule. And I think we can apply it to now our square root problem, and then maybe kind of see how the error of this trapezoid rule compares to the error of midpoint rule. Like, which rule is better to use, like practically, and how theoretical formula of trapezoid rule is going to compare to. So I'm going to just apply this formula for my function f equals the square root of x, and for my interval from 0 to 4. Sorry, my 4 looks like 1. And for my number of steps equals 4. So let me have, I'm going to write down T4. T shows a trapezoid, 4 shows number of steps. And my step here is going to be what? H equals 4 minus 0 over 4. This is B, A, and over number of steps. That's still 1. 1 over 2 here, because there's 2 from these averages for area of trapezoid. And then my first point here is going to be, well, like for interval, let me draw that square root. For interval from 0 to 4, my first point is over here. Second, third, fourth, and fifth. We are going to have total 5 points. So that's going to be a square root of 0, right? Plus 2 square roots of 1, plus 2 square roots of 2, plus 2 square roots of 3, and plus square root of 4. Last point is just by itself. And let's kind of calculate it. What we are going to have at the end. Square root of 0 is 0, and that's just 2, right? Plus 2 square roots of 2, plus 2 square roots of 3, and square root of 4 is also 2. I think we can kind of cancel 2, 2, 2 from everywhere, and we are going to have 1 plus square root of 2 plus square root of 3 plus another 1. We are going to have 5 point approximately. I'm going to keep 4 digits. 1, 4, 6, 3. 4 digits. That's estimation of trapezoid rule. Now, let's see if it's better than midpoint rule. See if it's better. We'll need to go back to midpoint rule. What midpoint rule gave us last class? Yeah, returning back. Here we have 5, 3, 8, 5, 3, 3, 8. So I'm going to write it down. I'm sorry that I'm scrolling. So compare to M4, which was 53838, and actual value, exact value of the integral, which was, remember, 53333. Well, you see that there is some difference, but it's definitely better than left hand estimation and right hand estimation, right? If I calculate error of trapezoid rule ET, I'm going to have 533, my actual value, exact value, minus T4, which is going to be 533 minus 51463. It's going to be 0.187. Well, what midpoint rule was giving if midpoint rule was equal? We need to scroll up and look at like what it was for midpoint rule. That was the formula for midpoint rule. It was minus 0.50505. Let's write it down. For midpoint rule was minus 0.0505. You see, despite the fact that approximation looks better on the picture, the error of estimation, if you compare it to actual value, precise value, is still kind of better for midpoint rule. The error is smaller for midpoint rule. Well, what is going to be formula for trapezoid rule? Remember the formal estimation. The formula, when you don't know actual value, is going to look very much like a midpoint rule. The only difference is going to be that instead of 24, you're going to have 12. Uh, uh, for comparison, error of midpoint rule is going to be you see that actually estimation of error for midpoint rule is twice better than estimation of trapezoid rule. And we see that it's even more than twice better in our like experimental result. Well, unless I did a mistake somewhere. And which hopefully I didn't, but who knows. Okay, so that's going to be actually the case. If you have a choice of either two methods, midpoint rule or trapezoid rule for your function, unless you have a very, very special case, midpoint rule always going to give you better approximation. Okay. Now, guys, let's concentrate on the formula and why people need the formula and how people use the formula. Usually, guys, of course, if you do know precise value of the integral, no one is going to do estimation because it makes no sense. You just know precise value. Why do we need the estimation? Of course. So usually there is no way to calculate it using like precise value minus your estimation. Usually what you do, guys, and how actually these formulas are used. Usually you estimate my error is less than this. And I do want error, for example, I do want error to be less than 0.1 or 0.01. Then if I make this number less than formula, then my error is going to be less than what I need. I want my error to be less than 0.01, for example. So I can use my formula. Sorry, place the formula. My formula is supposed to actually squeeze over here in between. Let me erase it and rewrite it. Not making very logical pattern. Okay, let me write it down one more time. I know that my error, according to the formula, is supposed to be this. If I make it less than what I wish, for example, this, that's what I want actually to make my error. So if I make this value less than what I want, then my actual value, because it's less than this expression, is going to be less, of course, than this. So EM is going to be less than this, because actually EM less than this, and that's going to be less than this. It looks like lots of this here. Well, what is going to give to us? Guys, if you look at this formula, usually you can find the second derivative. The case with the square root was not very successful because the second derivative was going to infinity at 0, right? But normally you are not going to have this. So you can find this from the given problem. Usually accuracy is going to be given. And the only thing which is not given is number of steps. So we use approximation formula to find how many steps we'll need to do to get certain accuracy. And you probably will ask me, why do we need to know how many steps? Why don't we use always 4? Well, you see that 4 still gives us some errors, right? And if you use more steps, the error is going to be smaller, just because, like you see that number of steps sits in denominator. So if we, for example, use 100 here and then square it, that's going to give you 10 thousandths denominator and much smaller value in total for the error. Of course, more steps is better to do for any estimation. And even Riemann sum tells us bring number of steps to infinity. But usually if you use a computer or a calculator, you cannot bring it to infinity. So you are going to use a certain amount of steps. Usually, guys, amount of steps you use for numerical integration is always trade or bargain between round off error. Because when you do many steps, you are going to add many numbers. Each number in a computer doesn't have infinite amount of digits. It's usually rounded to a certain amount of digits, which are kind of either like a float or like double type. And every time you round up something, you are going to make a little error. And if you have, for example, billions of numbers added, this error can add up to something essential. So you don't want to actually bring number of steps to infinity if you do numerical calculation. So it's always like your decision, like how many steps is too much and how many steps is not enough to approximate the integral. Let me show you how it usually works on example which is used in the book. I'm going to estimate how many steps I'll need for midpoint rule to estimate the next integral. So how many steps we need to estimate integral from 1 to 2 of 1 over x dx. Well, what accuracy we are going to request? With accuracy, let me write it down. What was accuracy? With accuracy 0.123. Let's make 4. Kind of, if you want to know for sure 4 digits of this value, how many steps do we need to do? Or what is supposed to be n between 1 and 2? So how many steps? We're not going to do those steps. We're just going to estimate how many steps we'll need, okay? So let's first kind of find out what the formula is going to give us, because that's accuracy. And usually accuracy goes on this end of the kind of expression. So I'm going to write down the expression. K b minus a cubed over 24 and squared. Somebody gives us that it's supposed to be m rule, because for different rules, the formulas are different. It's supposed to be less or equal than 0.1234. Again, if formula is less than this one, then actual error, which is less than formula, is going to be less than the number. Okay? So what we do know for this formula already? We don't know k yet, but we know b and a because they are just limits, right? We don't know n. Well, we just need to find k. We know that k is kind of greater than absolute value of second derivative of my function on the interval, in our case, from 1 to 2. So we'll need to differentiate my function 2 times. You see, here we have 1 and 2. We don't have 0. The function is not nice again. At 0, it's going to be not continuous, going to infinity. But because we are not integrating at 0, we are not going to have any problem with it. So I'm going to calculate the first derivative. Well, let's write down the function first, because usually people have problem like what is the function and what is the derivative. Function is 1 over x. The first derivative is negative 1 over x squared, right? What is going to be the second derivative? The second derivative is going to be, well, minus 2 over x cubed, and we are going to have 2 over x cubed. Well, guys, here we are lucky, and our second derivative is positive. Why? Because my first derivative was negative, was minus 1 here, minus 1 here. But this is minus 2, and when we differentiate it, it's going to jump in front and combine together and give me just 2. So my absolute value is still going to be this number. If it had minus, you would need to drop it. What is going to be the maximum of this function? Well, usually, guys, we're just going to draw the graph of the function and kind of see what is going to be the maximum on the interval from 1 to 2. Visually, usually function is going to be pretty simple. So you see that on interval from 1 to 2, maximum is going to happen over here at 1, right? And for us, maximum value is going to be just equal to 2. You can take 3 or 4 for your convenience, because actually formula tells that it's any number greater than second derivative. It's not necessarily supposed to be equal to the maximum of the second derivative. We're going to use 2, but you can use 3 or 4. Now let's plug all our numbers into the formula. So we have 2 here. My numbers are 2 minus 1 cube. Denominator is 24. We don't know n. We are going to keep it as n square, and we are going to keep our accuracy over here. Okay, so here 2 minus 1 cubed is 1, 2 here and 24 cancel a little bit, and I have 1 over 12 n squared supposed to be less or equal than 0.001. Well, how do I solve this? Well, remember that you can deal with inequalities like with normal equations. Just remember, if you multiply by minus, you have to change the sign of inequality. Here, nothing is negative, so we even don't need to bother about this. What I'm going to do, guys, I'm going to bring n squared here, and I'm going to bring this one, this expression in denominator here. So I have 1 over 12, 0.0001 n squared. And usually, guys, your number is supposed to be greater than something. That's just like correct direction of inequality. Well, to find n, we are going to extract the square root of our expression, right? And n is going to be greater or equal than, I calculated it already, or a book calculated, I don't remember, 40.8. Well, what should be your n? You can choose n 41 because it's supposed to be greater or equal. You cannot use n equals 40.8 because n is the number of steps. You cannot use 40.8 steps. Do you have to use such a weird number n like 41? Should we use? Well, usually, guys, of course, it's more convenient to use something round. Round number is, for example, going to be 50 or even 100. You're supposed to understand, bigger number here is going to make your approximation better. Just you're always supposed to understand that bigger you make it, your error from round off is going to be bigger. But if you increase it by 10 units, it's not going to, of course, increase essentially. If you increase it 10 times, maybe it's going to increase. So I'm going to write down we can use, for example, n equals 50. Or you can just directly use n equals 41. It's going to be a little bit complicated to use the midpoints of 41 subintervals instead of 50. For 50, it's going to be easier to find midpoints. Okay, guys, so we talked about trapezoid rule and we decided that the rule is not better than midpoint rule, so we're not going to even memorize the formula for it. You just remember that error is twice actually bigger than like midpoint rule. Now, I promised you to tell about Simpson's rule. Simpson's rule is estimating areas under parabolas. And why it's better? Because it's going to give us better accuracy. Let me kind of just briefly explain what is Simpson's rule. I'm going to draw a picture and give you the formula. Guys, it's not very difficult to obtain this formula. In your book, they actually do obtain the formula and show a very simple way to obtain the formula. But if I start doing all the formulas from the book, it's going to take me forever. So I'm going to show you approximately how the method is working. So if your function f of x is looking like this, you can take like 3 points and build a parabola on these 3 points. Just because parabola has three coefficients. Remember, parabola y equals ax squared plus bx plus c. It has three free coefficients. If you do know 3 points on parabola, you can actually find these three coefficients. So basically, if you do know 3 points through which parabola goes, you can find out this, and this. So you can always build a parabola on 3 points of your choice. And then you can build another parabola and another, and as many parabolas as you wish. How the formula of estimation is going to look if you build actually instead of rectangles parabolas. And you see parabolas are fitting a little bit better. But again, it's going to depend much on how your actual function looks. Sometimes parabolas are not going to fit better, but in most cases, yes. So usually it's a, and here x1, and that's x2, and more points, and parabolas are built on like ends of the interval. Imagine that you divide again your big interval from a to b into n subintervals, and it's b minus a divided over n step or size of subinterval, right? And how the formula of Simpson's rule is going to look. The integral from a to b of f of x dx is going to look like h over 3, the size of subinterval. In some books, you're going to see delta x. You can use delta x, I don't mind. And what is going to be in parentheses? F of a. Then for f of x1 plus 2 f of x2 plus 4. Already missed 4 here. Let me go over this direction. Plus 4 f of x3 and plus. And eventually the last one is going to be f b. So formula is going to have, looks similar to trapezoid rule. Just instead of 2 is going to have 3 in denominator, right? And the pattern is not going to be 1, 2, 2, 2, 2, 2, 1, but it's going to be 1, 4, 2, 4, 2, 4, 2, 4, 2. Why do we have this pattern of 4, 2? Well, because some points are going to be in the middle of the parabola, and some points are going to be the points between two parabolas, which are going to kind of increase amount. And some points are just going to be end points, like points A and B. This is my B actually, looks like 6. Yep. Well, let me write down the error bound for Simpson's rule. Okay, so you can compare maybe the like accuracy. So error bound for Simpson's rule. You don't need to memorize this formula. The only formula I want you to memorize is error bound for midpoint rule. Okay. So that's going to be k again, and then b minus a to the power of 5, and in denominator 180 over n to the power of 4. And k is going to be greater or equal than maximum, I think, of absolute value of fourth derivative. Yeah, I think that's a fourth derivative. 1, 2, 3, 4 on interval from A to B. Yeah. So if you look at this expression, You probably are going to notice n to the power of 4. So actually, increasing number of steps is going to decrease the fraction a lot, right? You still have b minus a to the power of 5, but usually it's not a big interval, and it's under our control. And the derivative can be large, but like usually this large coefficient and denominator is going to overwhelm it. What I want to do, guys, I want to do just estimation of error um, for our like 1 over x function. Just see like what is going to be error if I consider function 1 over x and kind of plug everything into this formula. Let's imagine that we are going to have n equals 4, and the interval is from 1 to 2, and that's 1 over x dx. Just like estimation of this error. Let's see how it's going to look. So what do we need to know here? We know everything for the formula. We just need to figure out what is k. K is a fourth derivative, right? We already know that the second derivative of 1 over x is going to be 2 over x cubed, right? The third derivative is minus 6 over x to the power of 4. And the fourth derivative, the function is pretty simple. It's going to be 24 over x to the power of 5. Still, the function is going to look like 1 over x. So maximum is going to be at 1, and minimum is going to be at 2. So I'm going to estimate k as like 24, or you can say even 25. You always can increase k because the formula tells that k is greater than that derivative. Let's plug everything in. So what is going to be estimation for this? So going to write down 24, and that's 2 minus 1 to the power of 5, 180, and 4 to the power of 4. What I'm going to have. Wow, let me see. So I have 24, 1. Give me a second, guys. I'm going to calculate the number. Okay, guys, I calculated the fraction, and the error is going to be 0.0005. So Simpson's rule, if you consider only 4 steps between 1 and 2, right, for function 1 over x. I calculated midpoint estimation. You remember the formula, it's k, but that's going to be a maximum of second derivative 2 minus 1 cubed divided over 24, number of steps squared. And that's 0.052. If you compare these two numbers, you see that error of Simpson's rule is like 10 times better than error of midpoint rule. So, well, why does it happen? Because we are estimating function better. Um, well, I think what I'm going to, guys, give to you to solve or to work, maybe at home, is a couple of functions to do the estimation. So, two problems. Sorry. So problems. Problem number 1. I wanted something about integral of 0 to 1 cosine of x squared dx. So what is going to be my question? How many steps n we need to estimate it with rule error less or equal 0.0001. So how many steps we will need in this division from 0 to 1 to estimate it with error 0.001? I'm not asking you to do actual estimation, just find how many steps we need, okay? And the second problem. I'm going to give you the table where we are going to deal with some unknown velocity depending on time. Imagine that somebody was taking measures of an object, maybe a car or something moving, and he could record the velocity of the object depending on time. So top numbers are times, and the bottom numbers are velocity at these times. Yeah, my maybe handwriting is not super nice. I think that's just kind of a book problem. Here, guys, can you use M rule and S rule to estimate S displacement, which is going to be equal integral of velocity of time dt. Basically, guys, here my axis t and v is going to be my function. And we are going to do it from 0 to 2.5 seconds, okay? Use midpoint rule and Simpson's rule. How many intervals do you have? 1, 2, 3, 4, 5. Not supposed to be too difficult. Just kind of plainly use M rule and S rule to calculate. Because for cosine, maybe it's going to be too complicated to use many steps, but here, not supposed to be too complicated. You see, something is given numerically, so we basically don't know what is function v. We just know the numerical value for it. But we still can estimate the area underneath, and this area is going to give us displacement actually over that time. Okay, I think that's all. And I'm going to give some extra credit problems for this section. I'm going to post them online. Okay. Okay, guys. So prepare these two problems and kind of, try to read the book.